started. So what I was asking is that is the greedy algorithm covered in your class? Greedy technique? Am I audible or because what I was asking is that is greedy algorithm covered in your class? I logged out. Hello? Hello? Can you guys okay. So actually allowing mic to everyone is kind of like if all of you are talking all at once, then it will be very hard to understand. So that's why you can say in chat. I am following the chat, so it's not a problem. Uh, so so greedy algorithm is not covered in your class. I don't know. It may be covered. So okay. So today I will discuss one of the application of this greedy technique. The first. Uh, okay, let me check. 7. Okay. So I have enabled mic for all of you. And check.
Yes, sir, it is okay. Thank
Yes,
you.
sir.
Yeah. So, okay. Okay. So let me share my screen. Okay. So is my screen visible? Yes.
Yes, sir.
Visible. Okay. Uh, so what I was saying is that we are today we will do an example, which is actually an application of this greedy algorithm. Today is 3:10. Okay. So today we will look at this problem, set cover problem. So I'll discuss what this problem is and how to find an algorithm for that. But the main focus is the greedy technique that I think have covered in your class. At least sir told me that he would cover, so I don't know. So I assume that you know the basic of greedy algorithm, at least how these algorithms operate. For example, like I think you have done some knapsack problem. So there is one knapsack problem you can solve using greedy algorithm. Uh, I don't know whether it's covered or not. There are a lot of algorithms actually that you can solve using greedy algorithm. It's a grid. Actually, you can say it's an algorithm, but it's actually a design technique. There are like a lot of algorithms are there that applies this greedy technique to design the algorithm. So this greedy technique, if you don't recall, it's same like we are looking at a problem. So I'm just giving a short recap of this greedy technique, and then I will move on to the set cover problem. So this greedy technique is what is this greedy algorithm? Okay, so what does it and like how we design these greedy algorithms? Uh, So it's basically, it also has kind of substructure type thing that we have seen in dynamic programming, but it's different. Like here we have a problem. Let's say you have this problem. This is your original problem, given input. Uh, given input, I mean, a problem consists of instances. So you can say it's better to write this as your problem. So this is your whole problem. Then you look at the sub problem of this one. Okay. Now, what we did in dynamic programming is that we solved these sub problems, and uh, we also like stored the solution in some table. And whenever there is a call of that sub problem again, then we use this table to access the value and directly use that one. So in that way, we are saving time or saving our time in recursions, right? So that was your dynamic programming algorithm. So here the technique is a little bit, it goes by its name greedy. So it's like at each step, you are choosing what is the best option for you. Okay. So when I'm looking at the sub problems, when I'm looking at the solution of the sub problems, I'll just look at the sub problem itself, whether it's optimal for that sub problem only. I'm not thinking about whether this solution will be accepted in the original solution or not. Okay, so that's kind of, we are hoping that our this choice that we have made, this would be in the optimal solution. So that's in that way you compute the whole, you solve the sub problems, and you combine the and you, and using them you solve the original problem. So this technique is called the greedy technique. Okay, you are just, you look at what's one sub problem, you solve it. You don't care whether this solution is optimal for the whole, for the bigger part, for this part, whether it's optimal for this part or not. You just care about whether it's optimal for this sub problem. And if it is optimal for this sub problem, it's fine. You take it into your original solution. Now you solve, like you divide this problem into many sub problems. You can divide. So you solve each of these sub problems, and you claim that, okay, I have this solution, I have this solution, I have this solution, I have this solution. Now you check that whether it's a solution of this one or not. So you can easily guess that it may not always result in a like the desired outcome. Like it may not be the optimal result. Okay, so greedy algorithm does not always work for any problem. It's not guaranteed whether it will work or not. But there are some problems where you can prove that greedy method is will give you an optimal solution. Okay, so this is precisely what the greedy technique is. It goes actually it's actually same as its name, as its name. So at each step you are choosing what is the best. Yeah, I mean, I am actually going to discuss this algorithm, and that there it's a very good example for understanding this greediness. So that's why that you'll see the set cover problem. Okay, so that's an example that I'll discuss today. Okay, so this is precisely the idea of greedy. Okay, so at each step you are choosing whether it's optimal or not for that smaller sub problem, and you don't care whether the solution will be the original solution or it would be in the optimal solution or not. Okay, so now let's focus on this problem. Focus on our problem, which is the set cover problem. So what is a set cover problem? So set cover problem is, I think all of you are familiar with sets.
Yes. Yes.
Okay, so sets. So think about a set. So the input of this set cover problem is a set S, and it's actually a tuple, and a family. F is a family of subsets of S. So how this F is a set itself. Okay, so it's a collection of subsets of S. Okay, there could be like some, uh, for example, I am bounding it. I should write it like, that's okay. You may not be familiar with this one. Okay, fine. Then be happy with this. Where and size of S is M. Okay, so this is our assumption that is the cardinality of the set S is N, and we consider a family of subsets. It's called the family of subsets of it. Family of subsets. Okay. So, for example, like you can consider this set. Okay, so think about this subset. Okay, so this kind of subsets. Okay, so this F could be this collection of S1, S2, S3, S4. Okay, so this F is a family of subsets of S. Okay, so by family we are so there is a basic difference between family of subsets and elements of the family and an elements of a set. So element of a family of subset is actually a subset of S. Okay, so each of these is a subset. These are subsets. Okay, so so I hope you get the idea of the input. Okay, so what are the inputs? Now the question is, the problem is, what is the question? The question is, does there exist, or let's say goal, let's say goal or output. We are looking at the optimization problem in here. So it's find a minimum subset of F, say C, such that okay. So what does it mean? I am going to clarify it. So it means that, in other words, every element of S is in at least one of the sets in C. Okay. So what do we mean by this? Let's see an example. What do you call it? This C is called a cover. So what do you mean by this? Let me explain. So we take the same example. If you think about the same example in here, I'm not going to then rewrite it. Just the color. Okay. So if you think about this set, so take a look at these sets. This S1, S2, S3. So if you take union of these three sets, S1, S2, S3, that would be equal to the set S, right? So, so this means that every element of S is in at least one of these sets, either in S1 or in S2 or in S3. So if you can consider a subset C, this subset C in the previous example. So in the previous example, S1 union S2 union S3 is equal to S. Okay. So if we consider C is a subset, uh, which is C is a subset of F. So C is a subset of F, mind it. C is consisting of this set, S1, S2, S3. Then it satisfies our property that every element of S is in at least one of these sets, either in S1, one of these sets in C, either in S1 or in S2 or in S3. So this means that C is actually C is called a cover, called a cover. of S. So cover in the sense that it's actually kind of like you cover every element by at least one of these sets. Okay, in that subset. So it's a very important problem actually. It has a lot of applications in very different areas uh, of like computer science. There are a lot of algorithms that a lot of problems actually designed based on these uh, problems, the kind of covering problems. You may encounter them later in your like maybe later in some courses you may be introduced with some kind of these problems, but okay, so base is this one, which is a very so it's also a very interesting problem. Okay, so the idea of cover is clear, or what is called a cover. So see the cover if it is like every subset of like every element of S is containing in at least one of these sets inside that set C. Okay, C is subset of F. Uh, it could be F, it could be the whole set, it could be the family that you have taken. That may be the only thing that you may have to cover. So it's depending on your family actually. It's not like it's not unique. Cover is not a unique. It's depending on what is the family. What are the families that you have chosen? For example, like if you think about the same set, okay, take the same set. Oh, sorry. So, uh, so you take the same set again. One, two, and you could have a different family. Your family could be okay. So let me write the sets. Your SO, your S1 could be S3 could be 7. S4 could be 1, 2, 5 could be 1, 7, 9. 9 is not there. 1, 7. Okay, so this kind of things. It could be your F. F is S1, S2, S3, S4, S5. So depending on your F, now you can see that you can cover like every element you can cover using this S1 union S2. Okay, so it depends on the family that you have chosen. It could be your C now. Okay, I'm not claiming that it's a minimum. It could be the minimum. Actually, I think it's the minimum in this case, the family that you have chosen. So this is not unique. That the cover is not unique. It's actually depending on what is the family that you have chosen. Okay, so now if you look at the question carefully, it asks for finding the minimum subset. Okay, so finding any C is not the solution. We need to find the minimum. So what is the way? I mean, can you think about, since I have already explained a little bit about greedy algorithm, and we are looking at the optimal, like we are looking at a sub problem and we are looking at the optimal solution for that sub problem only. So can you think about a solution that, and like, can you give an idea like how to approach for this problem? What is the first thing that come to your mind about this? Now you design. Now you want to design an algorithm. So okay, let me also clarify that. So now we want to design. So the task is design an algorithm that solves set. Now, so it's a very interesting thing. that if you can solve it, you'll prove $1 million problem in the world. Okay. If you are able to design an algorithm for this problem, for the set cover problem, uh, that can solve this problem optimally. That is, if you are able to find optimal set cover in polynomial time, then you would be able to solve. Uh, Actually, you have already solved a problem which is a well-known conjecture in computer science. I think you may know or may not know about that conjecture, P not equal to NP. Yes. So if you can design an algorithm for that, then for this problem, then you can uh, actually answer that question. Then you can say that P equal to NP. But so why am I saying that? Okay, so this means that there is no way we can design an algorithm to solve this set cover problem. That's actually true, but we can. So what we are trying to do is that we are trying to find an near like it's not the exact solution, exact optimal solution. It's kind of a like approximation. Okay, so you are going to very close or like trying to go to the close to the optimal solution. Okay, so our the algorithm that I'm going to discuss now, it may seem that it will result in a it will give you an optimal solution, but it's not guaranteed that it will give an optimal solution every time. Okay, so it's actually an approximation algorithm. So that is what is the meaning of approximation algorithm is that it's actually gives a solution which is some fraction of the optimal solution. Okay, it's some factor, like more than one factor, obviously, of the optimal solution. Okay, it's not exactly the optimal solution. So this is the first thing I want to clear, and I will show you that why greedy does not work. And there is an example. There are examples actually, and you can think of examples very easily if you like put some effort in there. Okay, so let's solve this problem first, and then I will discuss about this P and P and all that I have said, and approximation also. So let's first focus on the algorithm. Okay, so what is our input? Our input is this set and its family. Okay, so family has subsets of different cardinalities. Okay, so let's say there could be like uh, so what is the best choice? Like you want to cover the maximum number of elements of S in one go. Okay, so the first step, what we do is that we choose the maximum subset Sj of there is no zooming option in there. I think you can go for the full screen. In your screen, it's actually full screen in my tablet. I cannot expand it more. I mean, if I expand, then it will be difficult for me to write. Okay. Uh, okay. Okay. So maximum subset, maximum cardinality. I will describe the algorithm through an example also. Let's first think about the steps. Sj of F uh, that has okay. I'll write the pseudocode also, then it will be clear. So we choose the maximum cardinality subset. This is our greedy. So we are looking at this this all the elements in the F. We choose the maximum subset. Okay. Then it covers. Okay. So um, okay. So you choose the maximum cardinality subset. Now what do you do? You so that set choose a subset of F. So let's start with a empty set, and we include this in we include SJ in C. Okay, we include it. So now the next step is we just update SJ, update S. The SJ elements are already covered, so we don't need to cover them. We have to look at the remaining elements. So similarly, like this one, we also update. You can update uh, all the elements of F by Sj minus. So S, let's say Sk minus Sj, k not equal to 2. Okay, for the remaining elements of F, we do this operation. So that means now we are looking at a sub problem now, and then again we solve this sub problem. Uh, Again we repeat. Then you just repeat step 1 and 2, 1 and 2 till S is empty. Okay, so you keep on doing these steps. So what does it mean actually? So let's go back to our example again. Yeah. So and I just write some families. Okay. So what do we do? We first select the maximum cardinality subset. So this is our F. F is okay. So the first step is that we will choose the maximum cardinality subset. What is the maximum cardinality subset in here? These two. You can take any one of them. Okay. So let's say we start with S2. So we include this S2 in C. Okay. S2 is already covered. So what are the elements? 6, 7, 3, 4. I update my S. Now my S is 1, 2, 5, 6, 7, 3, 4, 1, 2, 5. Yeah. So my S is this one. And my S1 is just need to subtract the element 1, 2. S3 is 5. S4 is 1. 1, and S5 is 6, 3, and 4, 2. So the only set we have found is this S1. So we select S1. Now C is S2 union S1. Okay. So S1 is included. Now our updated age is only 5. And this would be 5. Rest of the sets won't be there. So there is only one set left. So C is S1 union S2 union S3. Okay. Okay. So this is the way you can progress. So let me number the steps. That would be it. This is the first step, and this is the second step, and this is the third one. So you obtain the solution within 3 steps. And if you have chosen S5, you would have obtained some other combination. Okay, so this is how this algorithm works. Okay, now what could be the optimal solution for this one? If you look at, so the question is now, is it optimal that of the solution that we have obtained by this for this particular problem only for this input S and this family F, is it optimal cover, or can you find a cover which is smaller than this one? I mean, what is the cover size now? It's a 3 size, right? S1 is union S2 union S3. So the question is that so since we are looking for the minimum cover, so the question is that can we like obtain a cover which is smaller than this one? You just observe this. This is a small example, so you can observe and find whether it's smaller or not, or whether there exists a cover smaller than this or not. So if you look at that this particular setup, A is equal to 1 to 5. Are you talking about this step? Yeah. So see, you so what do we do in the beginning? We choose S2 to be our set. Okay, because it's the maximum cardinality. Yeah, I'm going there. So S2 is of maximum cardinality, we choose it. Now, after choosing S2 in C, now if the elements of S2 in S, all these elements of S2 in S, that is 6, 7, 3, and 4, they are covered, right? They are already inside a set. We don't need another set to cover them. So it's ideal to just remove these elements from S also. Okay, so that's why we opt for S as this one. It's basically S minus S2. Okay, we just remove those elements that are in S2 because we don't need to cover them. Okay, now, yeah, so similarly, we updated this one also. These are like S1 minus S2, S3 minus S2. Okay, and similarly, like after we have chosen S1 in our set, S1 union S2. So if you look at S1 union S2, the only element left is 5. Hmm. So that's why this S is 5. Again, it's depending on my choice. If I have actually here the 5 will be like whatever you choose using greedy, 5 will always come. In the end, the sets are something like that. So you can try any combination, obviously maintaining the greedy algorithm. So you have two choices. Either you have to choose S2 or S5. You can take S5 and you can proceed accordingly. You will see that you ended up with 3 sets again. And your last set, whenever you are going to include the last set, it will be having like S equal to 5. So how S equal to 5 came? It's basically S equal to S minus S1 union S2. Okay. So if you do that, you will see that the 5 is only element that left. Okay. So that's why there is only one set left. So you can include it. Okay. So you can also check that this is an optimal cover for this problem. There cannot be a cover which is smaller than 3 cover the elements of S using that family of subsets that we have given. Okay. So in this case, we have obtained the minimum. In this case, we have obtained the minimum cover. I mean, C is the minimum cover actually. Not necessarily unique, but yes, minimum. It's one of the minimum. Okay. So now, okay. So in the beginning, I have said that there is no algorithm that solves this problem optimally. Mm, but we have seen that this algorithm results in an optimal solution for this instance. Now we are going to describe one instance or one input where this will not going to work. Okay, the greedy choice will give you some result, but uh, the optimal choice actually a different one. Okay, so it's very easy to make. Can you use like the same set? Okay, then okay, I'll make that example. But actually, it's very easy to construct that example. Think about even odd numbers. You can separate them in the family. And okay, let me construct. Okay, so dollars give final solution. So, so now I'm going to explain this claim actually. So let's take our set to be the same thing. So consider this family. Hmm. So in this problem, what like if you apply the greedy algorithm, what do? We'll go for the maximum element first, maximum size subset. Which one is the maximum size subset, maximum cardinality? This one, right? S3. So our algorithm will choose S3 first. So C will be S3. C, though in first step, C will choose S3. Once S3 is included, then the remaining set is oh, it's slight mistake. Sorry, it should be 2. Okay. So S is 2, 4, 2, 6. Hmm? Okay, no. In this example, wait, a little. I just have done a little bit mistake. Mm. This actually would give the optimal again, because 2, 6 if there, then you will choose this S2 and you'll get the optimal, because S1 union S2, I mean 2 is the minimum in this case. It will result in 2, but wait, I can design one that, yeah, S1, 2, no, S2 will be, S1 is empty. S1 is whole set in there, S3. So it's not that one. What I'm trying to do is trying to separate it from this 246. Compete it in size 26. No. Divide this even out. Okay. Okay. So there is actually a mistake in there. Actually, if you apply greedy, your S1 would be empty actually, and S2 would be 2, 6. S4 is 2, and S5 is 6 only. 6. Yeah. So S2 would be the next choice. So S3 union S2 is optimal. S3 is the maximum cardinality. That's why you choose S3. But yes, S1 union S2 could be the obvious choice. No, this is again an option where it gives you the optimal. Okay, let me just give me a few minutes. I'm going to construct this one out of this. So let me increase the cardinality by 1 of S, the odd numbers that are making the problem. Okay. Now I'm going to how S1 empty. Oh, see, this S1 is basically what? S1 is S1 minus S3. So S3 is S1 is a subset of S3. We can see. So S1 minus S3 is empty set. Then S3 is already included in there, and S3 is the maximum cardinality, so you include it in the solution. All right. Now, where are we? Oh, yes, I'm going to make that. Okay, now you can check this example. Okay. Mm, so my F is S1, S2, S3, S4, S5, S6. So okay, maybe 5. This one I am writing clearly. 5, 6. Yeah. So if you apply greedy, the first choice that you will make is this one. This is the maximum cardinality, right? So in the first, I will obviously select S3. Next, I will check all these sets. So this S1 would be empty. S2 would be just 4, 6. S4 is 8, 6. S5 just 4. And S6 is 6, 8. So S4 and S6 are same. So there are 3 sets that have the same cardinality. You can choose any one of them, and your S is upgraded to what 468. Okay, so in the next step, S3 union, you will choose one of these sets. So let's say you choose, if you choose S4, okay, so any one of them, you can choose any one of them. You choose S4. So S4 means that 8, 6 is included. So there is no point of considering this. So 6 is only common. So S2 is 4. S5 is unchanged, 4. And this, and S is 4 itself. So obviously you have to include, in the next step, you have to include, sorry, S3 union, S4 union, S, any one of these, S2 or S5, let's say S5. So this is your solution. This is your solution. Solution by greedy. Okay, but this is not the optimal. So here the size of C is 3, but clearly this is not the, actually it's should not be writing like this one. There is a notational problem. It should be this. Okay, it's not. These are sets as an elements, and that's actually notational problem. These should be sets. These are elements of that set. It should not be as a union. Okay. I should have been careful with that. All right. So this cardinality of C is 3, but you can see that you can manage to cover all these elements using S5 and S6 only, which is 2. So the optimal solution, but the optimal solution is S5. Okay. So this is an example where greedy is resulting in a incorrect output. Incorrect output means it's not resulting in the minimum output. It's a cover. It's always a cover. There is no doubt that the resultant output is will be a cover, but the minimality is not obtained. Okay. So this is the most important thing that we are asking, that uh, it's not minimum actually. So then the problem is that, okay, so it's not minimum, then how much like how far it's from the minimum, or like so how good, how close it is to the minimum one. That's the next question, and that's what we call the approximation algorithm. So this one is actually an approximation algorithm. Hmm. This greedy algorithm that we have studied for set cover problem, this is an approximation algorithm. It's not exactly an algorithm. So greedy algorithm does is an approximation algorithm. Okay, and I'm going to discuss like what are the uh, I mean, the approximation algorithm is somewhat like this, that I have given you an idea about it. Like it's it's like approximation means it's how close it is to the optimal solution. And there is a factor, there is an approximation factor associated with these approximation algorithms. So this approximation factor is a measure of closeness. Like this factor is a ratio of your solutions, and your solution and the optimal solution. And I mean, your solution means the solution obtained by the algorithm and the actual optimal solution, and it's the ratio of them. Okay, so obviously for minimization problems, this ratio is greater or equal to 1 in approximation algorithms. Like greater than 1 actually. Equal to 1 means we have obtained the optimality. Okay, so there is one thing, so let me write the pseudocode. Okay, file. This is non-empty. Start with an, we include I'm naming the maximum as SM. This SM, we include SM. Let's see, and C union, and then we update S to be S minus. Okay. So this is roughly the pseudocode. Uh, now the running time of this algorithm. Okay. So this running time is so what would be the running time? Okay, you guys can try this one. Now, what would be the running time? So the size of S is n. Let's say assuming that size of S is n, and size of f is m. So what is the running time of this algorithm? It's so at each step, what you are doing, you are just finding the maximum element, I mean maximum cardinality subset in F, and you include it and you update it, update your set. So and you keep doing it till your set is empty. So your set size is n. So this loop can run at most, the while loop, outer while loop can run at most order n time. And you have to check like intersection of these elements with S, which is like if it is there are m elements in S, right? If cardinality of F is m, so there are m sets in there. Checking an intersection with S that takes actually order n time. Okay, so this running time is order mn, order n number of iterations and order n number of checking to find the maximum. Cardinality subset in each iteration. So the running time of this algorithm is order mn. Uh, okay. Now, so is this problem clear to everyone, or is there doubt or any questions up to now? Because now I'm going to go to the approximation part and why, what is approximation? Okay. Okay. So there is another important note that it's set cover problem that I have told you in the beginning. This is NP hard. Okay. So this NP stands for non-deterministic polynomial time, which is kind of there are a lot of applications actually. This problem has applications in networking. I mean, the technique that you have. So see, set cover actually very useful problem. It occurs at it's actually I think set cover also has application in some data sets also. Uh, you can I think yeah, of course. Uh, First of all, this covering problem. This is uh, actually a covering problem. Okay, so you have a set and you're covering with some other set. So it's kind of what you call like you want to there are some networks and you want to cover some locations. Okay, that with that Wi-Fi network. Say, let's say you have some Wi-Fi connections. So let's say these are your points that you want to uh, like provide connections, and you need to find towers, Wi-Fi towers, to establish such that you can like cover all these areas. Okay, so deciding these locations, that where to put those towers such that you can cover those locations. This type of problems is actually a covering set cover type problem. Okay, it's type problem. It's not exactly the same problem. It's similar kind of problem, and similar type of approaches can be made to solve these problems. Okay, so and also I heard, I actually read about it, a very good application of this set cover, which is actually direct application of this set cover. I think it's about like managing data or something. Uh, yeah, it's kind of yes, yes, yes. So there are like sets can occur like in very different forms. For example, like there are also like you can think of a company that are like there are some different uh, skilled workers are there, set of workers, and you want to cover a certain task uh, optimally using the minimum number of workers. Okay, so this kind of problems actually can be dealt with setco. So it is very important problem, but you cannot like there is no algorithm that solves this optimally till now. So this solution, this greedy algorithm, this actually gives you a solution which is actually close. I'm going to show you how close it is uh, to the optimal solution. But this is like the base idea. Uh, I mean, the 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 implication of this algorithm is huge actually, because the factor is not that much large. The factor is some log in. Actually, this is a this greedy set cover. Next, I'm going to cover this one actually. That greedy set cover problem is what I call it's a log n approximation algorithm. Log n approximation. No, greedy means the choice. See, if you look at the algorithm first, what are you doing in each step? We are choosing the maximum size. So we are greedy about our choice. That, okay, I'm solving this right now for the maximum. I mean, I'm solving this problem with the best possible solution for the current situation. I am looking at this whole solution and I'm finding, okay, this one covers the most of the elements. I'll take this one in the solution. I'm not thinking about whether it would be in the optimal solution or not. Okay. So this choice is where I am not thinking about the future impact of this choice, and I'm making the choice based on just some observations that this is resulting in optimality for that scenario, and I'm taking it. That's a greedy choice because you are not choosing based on other parameters, whether you are not checking whether it's optimal or not. So that's why it's called greedy, because your choice method is greedy. You are not, your method of choice is greedy. You are not thinking the impact of that choice. Okay. So that's why this algorithm is not called greedy algorithm. It's actually the technique that we used to design this algorithm is called uh, greedy technique. We call this a greedy set cover algorithm. There are other techniques also to solve this set problem. You can use dynamic programming also to design solutions for this problem. Uh, but like for this part, just focus on this greedy technique that we have learned, because there are some problems which can be solved using greedy optimally. And there are some good graph problems actually. If you know about graphs, I don't know whether you know about graphs or not. There are like two, not two, there are many, actually, many graph problems can be solved using greedy technique. Uh, for example, shortest distance problem in a path. So you can think of shortest distance means that two locations are there. There are like many locations. Locations are connected by roads, right? So you can think of them as a nodes and vertices and edges. And there is a problem called there is an algorithm actually called Dijkstra algorithm, which uh, actually uses this greedy technique to solve to find the shortest distance from a source to another destination. Okay, but the like roads are having some weights. Weights means that your cost. Okay. So these are these are the greedy algorithms. It's a class. It's a not class. It should not be class. It's it's greedy is actually technique, and the algorithm that we design using greedy technique is kind of is called the greedy algorithms. Okay. So okay, so okay. Any other question regarding this set cover? Then I'm going to show the approximation. How close are we to the optimal solution? So it's clear that set cover does not solve this problem optimally. This problem is NP hard, and NP hard meaning is something that you will learn, I think, later in this course. Uh, and also one thing, that the algorithm that we have designed is actually called an approximation algorithm, and the approximation ratio is log n. I'm going to show you why it's log n. It's actually order log n. You can say order log n. Mm, I'm going to show you why. Okay, so for those who thinks approximation algorithm, okay. So approximation algorithm has this called approximation ratio, which is something like this, that if C star is your optimal solution, and C is the solution obtained by the algorithm, then if it is a minimization problem, if the problem is minimization, then your C could be less equals to some constant factor of this C star. This rho is some greater equal to one quantity. This could be any real number. So this rho is basically a element of R. It can be anything, but it could be greater or equal to 1. Mostly it's greater than 1. Equal to 1 means we have obtained the, if it is equal to 1, then we have actually obtained the optimality. So it's not equal. Definitely it's greater equal. It's greater than always. In these cases, where we know that the algorithm is not giving the optimal solution. Okay, fine. Now, okay, so this is the approximation ratio. So we show that rho equal to log n. Okay, for our problem, for set call. Okay, now, mm, how to show this? So to show this, first do this observation, that so if so if C star is optimal solution, then there exists a set that covers exactly that covers, sorry, not exactly, that covers at least this is the first observation. Why? Uh, so let's say if you have a set of 5 numbers, and let's say your optimal solution consists of this S1, S2, okay, just this two, then you can, so what you can do, so either one should be either here or here, right? So one goes to one of these places, two can go either one of these places. Each element has these two choices, that it can go to one of these places, right? So when you when you if you look at this S1 and S2, so if you start distributing those numbers, this 1, 2, 3, 4, 5, you put one in, let's say S1, you put two in, let's say S2, then you put three in S1 again, then you put four in S2, then you put five in S1 again. So that means that there is a set, there is a set that contains like at least more than one means more than like half of it. For example, what is 5 by 2? This is 5 by 2 is almost like 2.5 or something. So uh, this 2.5 you can think about at most 3. So if you distribute in that way, you will see that there is a set of cardinality 3 in our distribution, because it has to be either S1 is of cardinality 3 at least 3, or S2 is a coordinate at least 3. Okay, so this actually comes from the pigeonhole principle. If you know about pigeonhole principle, you can understand it uh, better. Do you know about pigeonhole principle? Oh, okay. So think about this. Uh, so there are like, so I don't know whether you are familiar with pigeons. Okay. Anyway, so think about this spaces, spaces where pigeon can stay. So there are like 1, 2, 3, 4, 5, 6. There are 6 spaces. So if you have 7 pigeon, then how many pigeons you can accommodate? And so no, sorry. Uh, so how are you feeling? That like if there is a space available, the pigeon will go to that hole, okay, or the space, okay. So obviously, if there is like more than 6 pigeons are there, then at least like one of the holes or space will contain more than one pigeons. That's basically the pigeonhole principle. Hmm. So similarly, like if there is like 8 pigeons, 9 pigeons, 10 pigeons, you can distribute them one by one, one by one, one by one, and there will be a hole where you have to do like n by k. So if so n by k means that 7 by 6 in here, it could be 8 by 6, depending on the numbers of pigeons. So if you have like n spaces and m pigeons, your number of pigeons m is greater than n, then you have to like, then there is a hole, actually there is a space where there is like m by n number of pigeons in there that contains. Okay, so this is precisely the pigeonhole principle. It's in discrete mathematics course. I think if you done with discrete mathematics course, or when you will do discrete mathematics course, you will encounter this one. So for this proof, actually, this idea was needed. Uh, okay, so if you don't know, then it would be difficult to understand for you. So is it clear? Like there are like if there are n pigeons, if there exist n pigeons, and m spaces, then there exists a space containing n by m number of pigeons. Is it clear? I mean, okay, if not, then you can assume that for now. Uh, so these will give you the, yeah. So this means that now we are looking at this problem in a in actually in a way that, say, let's say what we do in each step. In first step, we select some element. Okay, if we select a subset, the maximum coordinate subset, we select it, and then we left the rest of the part are there, right? So we are thinking about that rest of the part, like how, what should be the cardinality. So we know that there is a set having n by so one having like n by, so using this same thing, using this similar principle, there are like, you can think of this n pigeons as set elements and m spaces as your uh, m this elements, m subsets of S, which are inside the family, using similar argument, there exists and since we are talking about optimal cover, okay, so optimal cover will contain at least one of these elements. So not sorry, oh, mine. Well, there exists a subset oh, sorry. So there exists a subset that has at least n by C star number of elements. And this could be the maximum size. Okay, so whatever maximum size subset you have chosen, the size should be at least n by C star. Okay, so this means that in your first choice, you'll choose some subset that is of size n by C star at least. So the if the remaining elements, so this implies, okay, let's write. This implies that the first choice of the greedy algorithm is a set of cardinality at least n by C star. So, okay, we have obtained this. Now let's n1 remaining elements after the first choice that are need to be covered. Right? So what is this number? Obviously n minus. Now see, at least the size is n by C star. So whatever you choose, okay, that value should be greater than n by C star. So if you subtract it from n, that value should be always less than n minus n by C star. So it's n minus n by C star, which is n1 minus 1 by C star. You can think of in this way. Okay, so the rest of the element is always a fraction of this. Okay, same steps will be repeated in the second step. You always choose the second one now, but now you have already chosen a set, already chosen one element in the set. So in the optimal set, you also know that, okay, it's covered. That means if n2 is the remaining element, is a number of after the second choice that are needed to be covered. Okay, so so with the similar argument that there could be a set which will have this now our element is number of elements is n1. And the cardinality of that set would be at least n1 by c star minus 1. So you can directly write this one, that similar argument by similar argument above, we have this n2 is nothing but this n1 1 minus 1 by c star minus 1. Okay, why? Because there exists because there exists a set in n1 and the remaining, there exists a set in set uh, that contains at least n1 by c star minus 1 elements. Okay, so you obtain this, which is nothing but n 1 minus 1 by c star 1 minus c star minus 1. Okay, okay, so we obtain this one. Now we can write it as n into 1 minus 1 by c star square. You can check. Okay, so this means that there is a pattern for n2 square. So for ith element, it would be c star to the power I. And this is nothing but your exponential. So you can write it as n e to the power minus I by c star. Okay. So we have this. Now our ni is less equals to n into e to the power as I by c star. Now, what do we want to do? Like how far we will go? Till there is no element left. So we want this quantity to be 1, right? This should be 1. So this means n equal to e to the power I by c star. Hmm. So I equal to log n c star or c star log n, whatever. So this I is actually the number of iterations of the greedy algorithm, which is basically is the size of the cover. Okay. So the C that you obtain, size of C is basically I. So the size of C is equal to log n c star. Okay. So this is the proof. I think it's a bit difficult for you guys to understand, but for like clarity, you can consult this one. I mean, for the closure, actually, I gave the proof. This is the set cohort approximation ratio. The row is log n in here. Log n. Or order log n, you can say. Okay. So I think this idea is a little bit difficult for you guys. But like, nevertheless, I mean, can compare. Okay. So more or less, like the main things that I wanted to make sure that you guys have understood the set cover problem, right? There is no doubt in set cover problem and the algorithm that we have discussed, the greedy algorithm. I think these two are the fine. It's okay. You know the algorithm, you know the the problem, and you know that it's not the optimal, it's giving you some approximation ratio kind approximation algorithm, it's an approximate solution. So okay, so with this, let's move on to the coding part. Okay. Okay. So there is no other queries in here. I guess I'm not asking about the proof. I think proof could be a little bit difficult. You may read it in here, and if you find any questions, you can ask me later. Uh, okay. So if there is no questions, then I'm shifting to tutorial. Okay. So then going to shift to the coding. So for the coding part, actually, this is pretty easy. You can do it simply. I'm not asking using the sets because okay. So there is a thing. The implementation of this algorithm in C is actually I think would be a little bit difficult for you guys right now directly. Uh, why I'm saying this? Okay, so the question is that hashing. Do you know hashing? Hash function, hashing. Is it covered in your class? It's kind of it should be in the data structures, right? Array, strings. So it comes after that. Sorry, array, linked list, binary tree, and then hashing. So is hashing covered in your class? Hash functions. I think hashing is not covered because if so, yeah. So if so, then I would have done the coding for hashing. So actually, the problem is that um, why I'm asking about hashing is that you can see that here I have to perform this intersection of two sets. Okay, so this can be done efficiently using hashing. Hmm. Otherwise, it's difficult to design. Okay, so 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 I'm asking you to simply implement this one. Try to write a code. I'm not writing the code right now. It's for you guys. I'm giving you some time. Uh, what do? You just run two loops to check whether the elements are similar or not. Okay. So you can try this one, and I'm giving you like 20 minutes. It's easy. So you can think of sets as an array. I'm giving you the explanation. So you can think of the sets as arrays. You take that set as an array and the family of subsets. You can define each subset as an array. And whenever you are performing one operation, when you are including one set, you just use the comparison in a nested loop. Okay, that which element is like which one of them is having the highest cardinality. You can do it in using nested for loops. Okay, you can do it, but it's actually it will increase the running time. But since you don't know hashing and without hashing we cannot do that, so I'm allowing you guys to do that, do this one using the nested loops. Okay, so try. You have time till 5 20, 525, 530, 530. Okay. So try to write this code. Okay, the question, no, there is like, so what I was asking is that you guys, since you guys don't know hashing, implementing this set cover problem efficiently in C requires this hashing to perform these intersections. You cannot perform these intersections efficiently without hashing. So what am I suggesting is that you just use simple arrays, simple array to define this set and its corresponding subsets, and uh, also like write the code, and while like comparing while finding the maximum size subset, you have to compare the elements of that uh, set with the elements in S. Like you have to find the intersection, which intersection is the longest. So that you can do using two nested for loops. So I'm suggesting that you can use the for loops and you write the code of this set cover problem. Okay. So it's basically what I'm suggesting is to write the code for the set cover problem without using this hashing and any kind of like uh, other things. You can use structures also. But I don't know whether you are familiar with structures or not. Whether first hashing first, then these things will come. So okay, fine. So this is the task to write the code of the set color problem without using this hashing. I have given you guys till 5:30. Correct. Try to do it in C. It's Python. It's okay. I mean, you got it. But like, this class is for C programming, so you can try to do it in C. Okay, so this is the algorithm. I mean, this is the code. Uh, it's basically we are using a two-dimensional array in here, which actually corresponds to the sets that we are subsets that we are storing, and each subset size we are defining with this one. We maintain it with this array, and we also maintain two additional arrays to cover and to select which one is to be selected. Okay, so that's done with the chosen one. And here we just enter that array. It's nothing. Okay, now here the original part starts. Okay, so here till our n is positive, this while loop run, that like the loop that we have already done. That if you look at the pseudocode, you will see that the outer while loop, this one is the outer while loop, and in in this in between steps, we are just see. I told you nested for loops. So these are the nested for loops that we have used to compare the elements, finding the maximum one and selecting the maximum one, and discard the other. Okay, so this is a very simple code. Actually, you can check it. You can. I'm going to paste it in your in the chat. Uh, you guys can check it, and you can see it's not that difficult. I don't know why most people are not interested in C. Maybe that's why. But also, like, it's not efficient. This code is not efficient. There are there is actually a better way that I have told you using hashing, but we cannot do that right now. We don't know that till now. So when we maybe when we will do the hashing problems, or when we'll do the hash functions and all, then we can solve this part. Maybe. Okay. So let me paste this code. Oh, you take an example and based on that. Okay, fine. Such. Mm. Yes. Okay, good. Yeah, there is one. On that. Fine. Yeah, it's good. You can follow his code also. He gave a pre-input. It's just whatever the thing I wrote. It actually takes input from the user. So that's the basic difference. Otherwise, the baseline of the code is same. Okay. So fine. Uh, any other questions or queries? Okay. So this problem, we have done this example, and its corresponding code. Maybe we'll see a better one when we do the hashing. Uh, okay, fine. And then there is nothing left to discuss, I guess. That's around time. Yes, so okay. So there is nothing more to discuss. I'm going to stop sharing my screen now. Okay, so I assume that there is no doubt. So can end this class today in here. Thank you, everyone.